Good morning, everybody. It's wonderful to have you all over here. And on behalf of the Indian Society of Atomic and Molecular Physics, the Indian Institute of Science Education and Research, and the Indian Institute of Technology, both at IIT, it is my proud privilege to welcome you here for the 7th Topical Conference of the Indian Society of Atomic and Molecular Physics. So the Isamp, as the Indian Society of Atomic and Molecular Physics is known as, Isamp was a registered society. It was registered in 1981, and for almost, even before that, it started the biennial conferences. So in the last 4 decades, we have had 21 conferences in this series. And in 2005, Isamp started every other intermediate year a topical conference. So we have assembled here today for the 7th topical conference in this series. And it is great to have you all over here. Many of you have come from faraway places. I'm really grateful to you for taking the troubles. Travel is never easy. There is jet lag for the foreigners and travel hazards and difficulties which people coming from other parts of the India would have faced. I hope that your stay at the hotel is all right. We have tried our best to make arrangements. I'm sure there would be some shortfalls, so please excuse us for that. Both the institutions, ISER and IIT, we started functioning in less than 3 years ago. So we are really very young. We are still in our temporary houses. Both the institutions will move out of these temporary houses to another location about 20 kilometers from here. And our infrastructure over here is barely minimal. But a few years from now, at the main campus, we will have our principal establishment. And I hope that you will come back 5 years from now for another conference over there. This is a great field, atomic and molecular physics, and it has made a huge impact on engineering and technology in the last century. The field grew simultaneously with quantum theory in the last century, and in this century it is poised to provide some more breakthroughs because it will impact new materials, material science, nanoscience, and also life sciences. Atomic physics, in fact, was chosen, it was referred to by Richard Feynman, as many of you must be knowing. He chose the atomic hypothesis to be the most important single sentence to be handed over to posterity if in some catastrophe everything else would perish. So this field is of that importance, and it is very nice that we will have some very illuminating talks during these 3 days. The conference program is very tight. We will have about 50 talks during these 3 days and about 65 posters. So it is very important to keep to the timing. And our volunteers will help you with that. 2 minutes before the time is up for your talk, they will show you a red card. And 3 minutes prior to the yellow card, to the red card, they will show you a yellow card. So that will help you, sort of wind down your talk. For the keynote addresses, the time duration is a little more. So you will get a red card 5 minutes before the talk, and a yellow card even 3 minutes prior to that. So you'll get about 8 minutes, So this will give us some time also for questions and answers and so on. So main thing I would like to say is that the chairpersons will also help us keep the time, and I request all the speakers and all the chairpersons to help us in this process. Tirupati is a very famous temple town, and in 10 years from now, we will like it to be known as an education hub and as a major international research center. So your contribution today is a great start for this whole process. Thank you all very much. I will request Professor Ganesh and Professor Satyanarayana. These are the directors of the two institutions. The conference is enabled by the generous support from these two institutions. So first, I will request Professor Ganesh to come and welcome you on behalf of our institute. Professor Ganesh.
Good morning, everyone, dignitaries on the stage, and also the participants in the conference, people who have come from different parts of the world. I was told that about 20 scientists from outside India, they are attending the meeting, and all the other participants. First of all, let me, on the behalf of Indian Institute of Science, Education and Research, Tirupati, have great pleasure in welcoming you all for this conference on atomic and molecular physics. So this is the first conference that we are holding, and maybe it's also true with IIT perhaps. This is the first major conference that we are organizing, and of course together. And this is the hall. What you see is not really a conference auditorium kind of thing. It is actually a lecture hall for about 150 students. As it was mentioned, we are just about 2.5 years old, and we are just in our nascent stage in trying to establish even in a temporary campus. So it's a great moment of pride for us that even at this very early stage, we are able to organize a conference, and I must thank the Atomic and Molecular Physics Society for giving us this opportunity to organize a conference, and also for all of you for coming over here. As it was mentioned, Tirupati is a temple town, and I think for those people from abroad, I can say that it is the Vatican of India. That is an analogy I can give you. And now we have quite a few institutions which are coming up, particularly IIT and ICERs, and they're going to become educational hubs. And for most of you in the audience, you have heard of IITs, but you may not have heard of IISCRs, or Indian Institute of Science, Education and Research. These are new chains of educational institutions established by Government of India about somewhere in 2005, about 12 years back. And now we have 7 of them. Pune and Calcutta started in 2006, and I had the privilege of being the founder director of ICER Pune. That involves right from the beginning, from the first brick, you have to establish everything. And so very recently I was asked to come and do it all over again in Tirupati, using my experience, and hopefully I would certainly try to do it probably even better than what has happened in Pune. And we are institution ICER. The main thing about the ICERs are there are 2 things. One is they are research-driven undergraduate education, and the second thing is to teach science in a holistic manner. These are the 2 prime principles. So we offer a 5-year integrated BS-MS degree. We take students after 12 years of schooling. It is an all-India selection, and the 7 ICERs, we have a joint admission. We admit students on an all-India basis, and they have the choice of joining any of these ICERs, and we have a method by which they are allocated. And at ICER Tirupati, we started in 2015. The first year we had about 50 students or so. Next 75, and this year we have taken about 100 and odd students. So we have a total students population of about 250. We have about 30 PhD students and about maybe 10, 12 postdoctoral. So we are right away moving in the right direction to have a research-based science institute. I think having PhD program and postdoctoral program at a very early stage is very important, because the undergraduates will get a chance to study in a research ambience. Building a new institution, it's a big toll. Overnight everything will not be there. So it has taken us 2.5 years to get this space and do the minimal things. But as I said, we are already on the move. We have equipping the research laboratories in the area of physics, chemistry, mathematics, biology, and also earth and climate science. So we have, as Prof.Deshmukh mentioned, this is the first time we are attempting even having all this audio set up for the lectures, everything for the first time, and I hope everything will go fine. And if there are any lacunar drawbacks, please excuse us. And if everything works out well, give credit to Professor Deshmukh and team. If something goes bad, I take the blame for that. And I hope all of you will enjoy the science part of it. And also, I'm sure they would have arranged good lunches and dinners, which are equally important, because many times a lot of things happen over lunches and dinners, more than what happens in the lecture halls. So with this very brief remark, before a yellow card is shown to me, I would like to again take this opportunity to welcome all of you for this meeting, and I hope you will have a very, very productive meeting in the next 2 days or so. Thank you very much.
Thank you very much, Professor Ganesh. The lunch is going to be mostly a business lunch, and I certainly hope that a lot will happen over lunch, but it's not going to be very formal. So, nevertheless, thank you very much for your kind words and support. May I request Professor Satyanarayana to welcome the gathering, Director of the IIT Tirupati.
Thank you, Professor Deshmukh, dignitaries of delegates. Welcome. I would join Professor Deshmukh, Professor Bas Bapat, and Professor Ganesh in welcoming you to Tirupati and our two institutions. I'm basically a civil engineer who is come here to start the new IIT, so let me not talk anything about atomic physics or molecular physics. I'm as on the practical aspects at the other end of the spectrum compared to you guys who are more at the theoretical end of the spectrum. But it's a great opportunity for our two institutions to work together, as Professor Ganesh has pointed out, from the beginning when we started. In fact, we had our foundation stone for both institutions laid together. But at the same time, we had 3 union ministers, the chief minister, all of them come together. And the foundation stone for IIT Tirupati and IISER Tirupati and another institution that's coming up in Sri City, Triple IT, they were laid at the same time together at the IISER site. So that itself, this was before we started. We started our operations, both institutions started our operations in August, and this foundation stone was laid on March 28th in 2015. And since then, we have been, trying to leverage each other's resources, strengths, and how to take things forward. And we see it as a great opportunity. The topmost the science institutions, so that is IISERs and the campus here, and the top engineering institutions in the country, the IITs, and the campus that's been set up in Tirupati, coexisting within 3 kilometers of each other. I think it creates a great opportunity. In fact, we've been talking about creating common academic calendars, our students going and taking courses there, their students coming and taking courses here, and then taking up joint research initiatives together. They focus more on the fundamental sciences part of it. We focus more on the engineering and the applications part of it. I think it's a great synergy that is possible. I recall the roots of this conference when Professor Deshmukh last year, when we had the Indian Science Congress taking place here in Tirupati, where we had about 11 Nobel laureates, I think, came here, and then we had the Nobel laureate Sergei Harosh, the 2011 Physics Nobel laureate. He had come to IISER, visited IISER here to give a talk, and our students, a lot of our students came and participated, and then we had an opportunity to interact with him considerably. That's when he came and talked to me, saying that we would like to hold this conference, and he's been in a discussion with, you were earlier the president of this association earlier, so he hosted the conference in IIT Madras earlier, and so on. So I said, it's a great opportunity, yeah, please, let's go ahead and do it. And so this is the first of the many more joint conferences that we propose to host between the two institutions. We had, IIT Tirupati has hosted another international conference earlier last summer, 2016 summer, on sustainable technologies related to batteries and so on. It's good to see the group, very active. I understand they were founded sometime in 1981. The group came together and has been active every 2 years, holding a conference, and then the topical conferences, as you mentioned, every other year again. This is the 7th topical conference with the this time the focus on quantum collisions and atomic and molecular species and photons and so on. Of course, every conference we have a theme, but not necessarily that all the papers are exactly along those themes, but the broad area of your atomic and molecular physics. The other thing that they were keen on is to host it at both the places. So today you're having your sessions here, tomorrow at IIT Tirupati, and then you're back here day after tomorrow to wrap up things. So that's another good thing, and people have worked together. I've seen a lot of effort going into hosting this conference. So have a great stay and a good conference, and let us know how we can support the initiatives that all of you plan to put together and take them forward. Thank you very much. All the best. Yeah.
Thank you very much, Professor Satyanarayana. We have two keynote addresses in this inaugural session. One from a theorist and another from an experimentalist. So the theory keynote address will be given by Professor Anatoly Heifetz from the Australian National University, Canberra. He is a leading expert on coherent control of quantum mechanical systems, Attosecond, time-resolved atomic dynamics, atomic ionization in super strong laser fields. And then we will have the second keynote address from our experimentalist expert, Professor E. Krishnakumar. And it's very nice to have both of you over here. Professor Krishnakumar is a leading expert on electron molecule collisions, photoionization, photodetachment, negative ions, electron and ion momentum imaging, electron controlled chemistry, and so on. So it's a great privilege for us to have such distinguished scientists address us at this inaugural session. So we will begin the inaugural session now, and let me invite Anatoly for the keynote.
Good morning, ladies and gentlemen. I'm extremely privileged to be here and to open this wonderful topical conference. My special thanks goes to Professor Deshmukh, who invited me to give this talk, and it gives me pleasure to meet him in person because we've been collaborating for many years, and it's very nice to meet him and his extended group and his students. We authored together many, many papers, and now I can actually shake hands with all of them. This is the title of my talk today. And the idea of this research is to trace electron motion in atoms and molecules on their native time scale, which is incredibly short. It's 10 to minus 18 seconds, so 1 attosecond. And the idea is looks incredibly simple. You shine a short laser pulse on the atomic system, and then you wait with a stopwatch and wait till the ejected electron arrives to your detector, and you figure out how much time it takes for the electron to arrive. And before recently, this was not possible at all to do this research because the time is very short. You don't have a stopwatch like this. But now, over the past decade, with the development of the laser pulse technology, it's actually experimentally possible. This is something which is called ultra-fast science. For two reasons. Reason number one, these processes, they happen incredibly fast on a very short time scale, but also it's very rapidly developing field of science, and I'll show you some graphs. So it's a frontier of atomic physics, and one of the most dynamic and rapidly growing part of atomic physics. I will show you in the following some original results, but main purpose of this talk is, of course, pedagogical, because I see so many young faces in this audience, and I want to entertain, enlighten them, and provoke to do something incredibly interesting. So that's the main purpose of this talk. At the same time, I see some faces, I know some people who do this professionally, and of course they know this field in much more depth. So I have to strike the balance between originality and the breadth and scope. So it will be a mixture of both. This is my recent affiliation. I now spend some time in Frankfurt as a guest professor at Goethe University, but my main affiliation is, of course, Australian National University in Canberra, and Canberra is the capital of Australia. what's the motivation of these studies? And motivation, of course, it has its historical roots. It's actually, we can think of extension of something which has been known for several decades, which is known as the femtochemistry, transitional states of chemical reaction studied with the short laser pulses. And the idea is you shine laser pulse on your molecule, and then the molecule goes to excited states, and then cascade of transformation, and you shine flashes of laser light, and you know how these short-lived transitions take place, and finally you end up with some equilibrium state which is different from initial state, and you know how chemical reactions actually proceed. And for doing this, you get a Nobel Prize. So the idea is to repeat something, but on entirely different 3 orders of magnitude shorter. Femta is 10 to minus 15, and if you want to do this in atoms with electrons, you have to add or subtract 3 orders of magnitude in time. And the idea is very simple. Attophysics is attosecond laser pulse generation and the application to studies of electron motion in atoms, molecules, and solids. And this is something which is I have not invented. It's actually citation. There is a Thomson Reuters, they award a citation laureate award. And this citation laureate award is historical precursor for the Nobel Prize. And in 2015, it was awarded to Attosecond science with this citation. And the idea is we generate these short pulses, and then we shine these short pulses on electrons and see how dynamics of electron ionization takes place. And if you look at the number of papers with as it goes, as this log scale actually, since conception, since the first paper on this topic, this is the second science of femtochemistry, and that's where the Nobel Prize was awarded. So Attosecond science, Attosecond physics is a little bit behind, but unfortunately for Attosecond science, there were some major discoveries like gravitational waves, but otherwise I'm sure they would make it to the big one. So the motivation is quite obvious for this research, and Web of Science Citation Laureates 2015, who knows, maybe in a few years they will make to the big one. This is outline of my talk. I will talk about major concepts of this Attosecond science, and one of these key definition is Wigner time delay. I will say about a few experimental techniques, how this can be measured. I also provide some theoretical interpretation, either by solution of the time-dependent Schrödinger equation or more physically transparent, but in the weak field limit, we can actually get away with lowest order perturbation theory. There will be some case studies, and there are also historical case studies. The first experiments were done on noble gas atoms, but they actually now extended to molecules, and molecules, they provide much more complexity, but much more, much richer physical picture. And I'll give few examples of recent work on molecules which I was involved. There is another concept which is tunneling time delay. With Wigner time delay, there is a consensus. People more or less agree what it means and how it's measured and why it's so important. With tunneling time, it's still ongoing debate, and actually it's very hot topic. The difference between these two concepts depends on the regime of strong field physics that we are probing. In this strong field physics, there is a universal parameter which is called Keldysh parameter or Keldysh adiabaticity parameter, and tunneling time refers to the different regime as compared to multi-photon regime, which refers to the Wigner time delay. Experimental technique is called Attoclock, or angular attosecond streaking, and the case studies I will select is the zero tunneling time in hydrogen atom, and it refers to very recent, still unpublished experiment, and we are fortunate there will be another talk on this topic, so we will know this with much greater detail. And of course, I'll say a few words about the outlook of this research. Wigner time delay was actually introduced by Wigner 60 years ago, and it was referred not to laser science, it was referred to electron scattering, and Wigner considered potential scattering of S partial wave, and we know that if you throw the plane wave on the scattering potential, there is a phase shift in this scattering, and the outgoing wave, it acquired this phase shift, and if this potential is dispersive and phase shift depends on the energy, there will be group delay. The wave packet arrives to the detector with some delay relative to the propagation in the free space. And this time delay, it's called Wigner time delay, and it's nothing but energy derivative of the scattering phase. So it refers to the group velocity of the wave packet. Now, this concept has been generalized. Historically, it was introduced in a PhD paper by Isamp, dated 1948, and these two papers are very widely cited in Attosecond science, and sometime the Wigner time delay, it goes by the name Wigner, Isamp, Wigner, Smith time delay, and Smith actually generalized this concept of Wigner time delay to arbitrary partial waves. He introduced scattering matrix, and this scattering matrix can be either single channel and single dominant channel, then it's just simply energy derivative of the phase in this scattering channel. But if it's multi-channel, then there is something which is called lifetime matrix, and it's constructed from the time delay in every given channel. So, and this was generalization 5 years since Wigner time delay paper. So now they're talking about Isamp, Wigner, Smith time delay. Now, that's how it goes. Also, by famous paper of Fana, this concept can be generalized to scattering states. In scattering problem, time delay has a very transparent physical meaning. It's called dwelling time. So the particle arrives to the potential. It's captured by this potential. It forms quasi-bound state. It stays there for quite some time, and then it goes away. And the time it spends in this quasi-bound time, it's called dwelling time. And if you extract this dwelling time from the Fana Wigner, bright Wigner Fana formula, then the time delay is inversely proportional to the dwelling time. This is time delay, and oh, sorry, this is the resonant width, and this is the time delay, or dwelling time. These are quite old developments, so it's late 50s, early 60s, and it was nothing but academic science. It was just some mathematical concept. No one thought about it seriously before very recently, when they managed to produce the laser pulses of very short duration. And the way they did it related to the tunneling ionization. So if you generate laser pulse, which can compete with forces of nature. So the electric field strength in the pulse should be comparable to the Coulomb field, which binds the atom together. Then the laser pulse can actually tilt the Coulomb barrier, and electron can tunnel out. So the laser pulses of this intensity, they were produced quite recently. And what people figure out that because the laser pulse has an oscillating electric field, the electron goes away, makes some excursion, but then when the laser pulse changes its polarity, the electron comes back and hits the ion, so it just simply recombines with the hole it leaves behind, and on the way out, it's accelerated by the laser pulse. So it acquires quite significant energy, and all this energy is emitted with a single flash of radiation, and this radiation can be tens or even 100 times larger than driving laser frequency. So we convert infrared laser pulse to XUV or sometimes even X-ray light. And because this can happen only with the perfect synchronization of going out and coming back, this flash of radiation is very short. So we can convert many, many femtoseconds of driving laser pulse to tens attoseconds of this XUV flash, and that's how they generate these laser pulses. So we start with 10 femtoseconds, but we end up with 100 attoseconds. So it's 100 times compression. And the idea is accredited to Paul Corkum for his seminal paper, and he was actually this awarded to this Thomson Reuters citation laureateship for this paper. Attosecond pulse, it's a nice toy, but there is a price to pay. You compress in time, you expend in energy. So even though these attosecond pulses can be generated quite short, 16 attoseconds, but the price to pay, 67 attoseconds, the price to pay it's huge bandwidth. So there is not much useful you can do because of this very large spectral bandwidth. But somehow they managed to produce something which is much nicer. Instead of isolated attosecond pulse, they produce what is called attosecond pulse train. And attosecond pulse train, it has two good things at once. We have a comb-like frequency spectrum, and if you convert it to time domain, there is no any loss, or it can be very short, tens of attoseconds, but spectral widths can be quite decent, probably few electron volts. So you can do very nice spectroscopy both in energy domain and in time domain, and it's a very nice feature. And most of the recent investigation in attosecond science were done with these attosecond pulse trains. This is the first measurement of Wigner time delay. It was done with isolated attosecond pulse. That's why they have to go to very large energy, because the energy spectrum was about 20 volt wide. So the idea was they shined the laser light on the near atom, and they ejected 2 electrons. So it's about 100 volts energy of this laser light. And they ejected 2 electrons, one from the outer neon shell, which is 2s, and another from inner, 2p and inner 2s. And 2 electrons, they went away. And they waited with the detector, and they figure out which electron arrived sooner. And it appears the 2p electrons arrived sooner to their detector. How much sooner? 21 attoseconds sooner. It was measurable delay because they claimed the error in their measurement of only 5 attoseconds. And that was the first atomic physics attosecond measurement. It's an incredibly important paper. It has probably close to 500 citations. I'll show you the number later. But the idea how it was done, it's done with attosecond strict camera. Very simple concept. They convert the time to the photoelectron energy. And the way it's done is the following. They shine this pulse with this duration. It kicks out the electron. And also, because this pulse was produced with a driving infrared pulse, they split out, attenuated to the different branch, the very same pulse, and they put it through the time delay line. So the driving pulse and ionizing pulse, they can be delayed in a controlled way with each other. And what happens, so depending on the phase of this infrared probe pulse, this photoelectron can be either accelerated in energy or decelerated in energy. So by changing the delay between a XUV pump and infrared probe, they actually converted the time delay to the energy. And they produced, they mapped the time of release to the momentum or the photoelectron energy. And these are two major bands. One is related to D2S electron, and another one is for the outer 2p electron. And you see that kinetic energy for the deep electron is less than for the outer electron. And then they just figure out what are the crest or peak position of these two bands are, and they appear to be shifted by 21 attosecond. So they claim the accuracy of this measurement is 5 attosecond. Now, why this happening? So it's very easy to understand that we model this process theoretically quite accurately, and it appears that electron motion happens without delay. You turn on the laser pulse, and the photoelectron starts going from 2s and 2p states simultaneously, and they form the wave packet at the same time. But what happens that when the laser pulse is off, you know that then propagation is in free space, crest position versus time is linear dependence with a constant speed. And if you backtrack this propagation to the origin and look carefully at the origin, it appears that backtracking of the 2s electron hits the negative starting time relative to the laser pulse, and backtracking of the 2p electron hits the positive time. And if you take the difference between the two, you get something close to 10 attosecond. Not 20, as they measured experimentally, only 10. But it's quite understandable because of the phases, of the scattering phases. We come back to the Wigner time delay concept. We just take the scattering phases in this potential, calculate the energy derivative, and for one of them, it appears negative. So it's not time delay, actually, it's a time advancement, it's acceleration. So we can actually interpret it more transparently, but I probably skip this mathematics. We would just form the asymptotic wave function of the photoelectron in the far region, and we just figure out that the crest of this wave packet propagates in such a way that the phase is stationary. That's very powerful concept of a stationary phase. If photoelectron wave packet can go in different trajectories or different paths, and phases oscillatory, different paths and oscillatory phase, it will cancel out each other. Only those trajectories survive where beating of this phase is not significant. They call this stationary phase. And the mathematical condition of the stationary phase is that the energy derivative is 0, and that's how you get the concept of the Wigner time delay in this stationary phase formulation. And it appears that trajectory of the photoelectron is such that wave packet group delay is calculated. This is Wigner component, which is energy derivative of the scattering states, and this is something which adds on due to correlation. So Wigner did not consider many electron systems, but for many electron systems, the process of injecting the electron may take some time, and it's encoded in this correlation-dependent amplitude. So this is the first or most seminal paper. As I said, it has more than 400 citations. And relative time delay, as I said, experimentally it was measured as 21.5 attosecond. And then many theoretical groups tried to reproduce these results, but they failed. Invariably, on theoretical sides, it was only 1/2 of this measurable amount, and it was a greater mystery for how many years? For 7 years, and much to our relief, now we know that the answer, 7 years later, another science paper, it's from N. Louis group in Lund, and they actually measured the time delay in a perfect agreement with the calculation. The first paper, they calculated at 1 photon energy, and this is the red point. This is old measurement, and this is the theoretical prediction, blue and purple. And you see that it was way off the theoretical mark, but new measurement from N. Louis goes right through the calculation. So most likely this measurement was incorrect. But you see, sometime in science, incorrect measurement attracts the largest number of citations, because people try hard and try again to reproduce it. They're never able to do it. They try again. You have lots of citations. But finally, there is somebody who come up and explain where the error was. And now, much to relief of many theoreticians, now we know that what we were doing was correct. Now, there is something, that was the first technique I showed you. It was the second streaking. And the second technique, it's called rabbit. It's a crooked rabbit with double T, and it's an acronym for reconstruction of attosecond beating by interference of 2 photon transitions. And this is the rabbit which is measuring time. And the idea is, again, it's a pump-prompt measurement. So you need an XUV pump to ionize your system, an infrared probe to measure the time. And it's done exactly the same way. You generate attosecond pulse with the infrared driving light, and you split your driver, attenuate, and delay, and you get a pump and probe with a controllable delay. And you shine your pump and probe pulses on your system, and the idea is that XUV laser light, or this attosecond pulse, it comes in harmonic numbers, and these harmonic numbers are always odd. Why they're odd? Because you absorb many infrared photons, and then you emit this light or this energy in single flash. And by the momentum conservation, you can convert only odd number of infrared photons to one fed XUV photons. So the number of this harmonic is odd. And if we have two harmonics energies, let's say 2q minus 1 and q plus 1, and then you add or subtract one driver, one infrared pulse. And then by adding one infrared quantum or photon to this harmonic, or subtracting one infrared photon from this harmonic, you end up with the same quantum state. And because you have two distinguishable quantum paths to this state, there is interference between them. That's the idea of quantum interference. And by changing the relative time delays between the XUV and infrared, you get something which oscillates with this time. And this even feature in the photoelectron spectrum, it's called sideband. These are harmonics, and this is sideband. And this sideband oscillates with the intensity depending on the time delay between infrared and XUV. And the phase of this oscillation, it contains the Wigner time delay. It also contains some instrumental group delay of the harmonics, because harmonics, they don't come at the same time. They delay with each other. That's why, and this is unknown experimentally. That's why to remove this uncertainty, they do these measurements in pairs. They measure one atomic shell versus another atomic shell. They measure one atom versus another atom. Now they even do this they measure time delay in one direction and time delay in another direction. The idea is to have a reference, to take the difference between two measurements. So then they can remove this instrumental uncertainty, and the relative time delay in argon, they measured with this technique, and because, as I said, the first measurement was performed as very large photon energy, 100 electron volts, because they have this uncertainty of energy spectrum. Because this was done with rabbit technique, there was no any significant broadening of the pulse, so they were able to do this close to ionization threshold, and they do this with quite low photon energy close to the threshold, but most importantly close to the Cooper's minimum of the ionization of the argon atom. And we know that Cooper's minimum has a significant variation of phase. It's actually variation of phase by 1 unit of pi on very narrow energy span, and significant variation on a short energy interval gives you large variation, large energy delay, and if you energy derivative. And if you look at the Wigner time delay, it goes into hundreds of attoseconds, many hundreds. And if you compare experiment with theoretical prediction, the blue one is the where the theory puts this delay, and this is 3 experimental points. And this one is right near the Cooper's minimum, where delay is huge, and it's quite significant variation. So it many times more than uncertainty. And since then, since 2012, there was no progress in resolving this issue, I'm afraid. So it's still outstanding problem. And Anne-Louise Lier, she was involved in this experiment, and I talked to her. She was happily resolved this controversy in the neon measurement. So she's very hopeful that finally they will be able to resolve this uncertainty, this controversy with the argon. But it's interesting object. Resonant Wigner time delay can be actually quite significant, and the most interesting example is what is called giant resonance in the semi-filled shells of transitional metals. And this is in manganese, but it's also in the whole row of periodic table. The idea is that because of the spin-up, spin-down coupling, the 3p shell, 3D shell in this atom becomes only partially filled, and there is a close proximity from the 3p electron to jump to this partially filled 3D shell. And because they belong to the same principal quantum number, it's a so-called super-Köster-Kronig transition. It's incredibly strong transition. And because they are inner shells, it survives in every phase. It survives in atom, in molecule, in liquid, in solid. So it's a huge transition. It has cross-section in 50 megabarns. I think it's the largest cross-section in atomic physics that I've ever seen. And the time delay, if you look at it, time delay can be actually in femtoseconds. It's 1,000 of attoseconds. So it's 1,000 times bigger than something which was measured before. Unfortunately, I lobby very heavily. I talk to many experimentalists, and I tell them, please measure this time delay. Its cross-section is large, delay is large, but it's work in progress. So, and solid-state physicists, they're very interested because they can do this on a solid surface, this measurement. As I said, they need to measurement to make a reference. And the latest advancement was to take a directional measurement. They measure the time delay in one direction and the reference relative to the time delay in another direction. And this is how they do this. They take the spectrograms in 2 directions. They have this oscillation of the sideband, and they make a comparison how the sidebands oscillate in different directions. And what is interesting that they start with a fully isotropic object. They start with helium atom. So there shouldn't be any isotropy in the time delay. They end up, after first photon absorption, they end up in a helium ion, which also in 1s state. It doesn't have any anisotropy either. But then they shine the second photon. And the second photon can actually end up either in D state or in S state. And these two states can actually interfere, and that's where they're getting this time dependence. Usually, there is a Fano propensity rule. All the atomic ionization goes from with increasing orbital momentum. So if we start with S, it goes to P, and by the Fano rule, it has to go to D. But we know that D electron has a what is called magic angle, where the spherical harmonic has a kinematic node. And then these two strong channel, which is suppressed by this kinematic node, and this weak channel, they become competitive, and they create this time delay anisotropy. And we see that this time delay anisotropy starts very soon after this magic angle, and that's how it should be. But if you take some other atoms, for instance, like neon, it has natural anisotropy because outer shell of neon is a p shell. So from p shell you can go to, and this is helium, and for neon from p you go to d, and from d you go to f and p, and because of these different symmetries of these orbitals, the asymmetry is significantly larger. So you don't have to wait and reach this magic angle. Your angular symmetry starts right at the very low angles, and it reaches significant number in hundreds of attoseconds. And we just wait before this measurement is taken. There is some preliminary data from Urzi Keller group, and we wait when they analyze it. What you can do also, you can actually measure the time delay difference between spin orbit components. If you take a heavy noble gas, and in outer p shell, because the electron spin and electron orbit can be oriented in two different ways, and magnetic moment introduced by this or current of the orbital motion interacts with spin in such a way that there is a spin-orbit coupling splitting, and that's how it showed. And in heavy atoms, in krypton, it's slightly less than 1 volt, but in xenon, it's nearly 1.5 volt. So it's measurable experimentally. So experimentally, they can actually resolve this spin-orbit coupling. So short pulses can actually resolve sub-electron volt spacing. So it's incredible. So attosecond time resolution and sub-electron volt energy resolution. And there are some auto-ionizing states where the measurement cannot be done or calculation is very jumpy because every resonance sends the phase up and down by 1 unit of pi. But outside this resonant region, there is a measurement and experiment, and they quite nicely agree for krypton. But for xenon, there are 2 points which are clearly outside any theoretical predictions. And it's very interesting to see there is some physics clearly beyond the model we used in this calculation. And there are 2 calculations. They make similar predictions, but nowhere near the experiment. So it's some work for theory to be done. Or, who knows, maybe the experiment is not correct. There was some historical precedent. But it's work in progress, and the question is still open. Molecules are much more fun because molecules, they inherently are anisotropic. You take a molecule like CO, and we know that that photoelectron going to the oxygen side and photoelectron going to the carbon side, they experience different potentials. Different potentials give different phase shift. Different phase shifts resulted in a different Wigner time delay. So time delay on the left is not equal to time delay to the right, and they call this stereo Wigner time delay. and they measure this on different sides of the molecules. If somehow there is an instrument which allows you to measure localization and velocity of the electron in a molecule, even though quantum mechanics tells you that it cannot do this, classical mechanics or semi-classical mechanics allows you to do this, and the instrument is called Wigner transform. And if you take a Wigner transform of several photofragmenting or dissociative states, you can actually see that electron is localized more on the carbon side, and in some other states it's localized on the oxygen side. And you imagine your state with your detectors on oxygen side and on the carbon side, and obviously if electron starts from oxygen side and arrives to the carbon side, it has to travel molecular distance. So it's much shorter. If it's ejected from the oxygen side, it's much easier or faster to arrive the detector on the oxygen side. And that's a very nice, very intuitive, very simple explanation of this Wigner stereo time delay, and it correlates with this localization of the emitting side on the molecule with the experimental measurement. And this is a very important result, because this is the first time photo effect is resolved in time and space. We can say that Wigner time delay measurements allow us to resolve photoelectric effect in time, but now it's resolved both in time and in space. So it's very important. Now, very short paragraph on the tunneling time. I have probably 5 to 7 minutes, but it's interesting. What I was talking about, it was very fast ionization going vertically. If we have a photon of not sufficient energy, but sufficient strength, then we tilt the potential barrier, and the electron tunnels out. And the tunneling time, it asks you the question, how much time electron spends under the barrier? It's a classically inaccessible region. Photoelectron kinetic energy is negative. Velocity is negative. Kinetic energy is negative, and velocity is imaginary, and time is imaginary. Classical mechanics tells you that time under the barrier is imaginary, so there shouldn't be any tunneling time, but measurements actually showed that there was some tunneling time, and there have been hot debate of finite tunneling time. There were several definitions, at least 4 definitions of tunneling time, and 18 reviews of the past 10 years. So it's an extremely hotly debated subject. And the way they measured it, it's called Attoclock, or angular streaking. They have circularly polarized light or slightly elliptically polarized light, and it's spinning around. The laser electric field is spinning around, and it's like X-ray tomography in a hospital. Your field is spinning around your object, and you project the image on the screen. And depending on the time it takes for the electron to eject, the screen, the image is tilted or rotated or offset on the screen, and this angle can be converted to the time delay with a good accuracy, 1 degree. It's about 6.7 attosecond. And that's how it's done experimentally. I don't want to go into all these details, but importantly, that's a big business. And these papers, they start producing papers from 2008, and they are very significant citation of this research. And they started with a quite significant intensity of the laser field, and at this time, at around 2010, they concluded that 0 tunneling time, but then they repeated this measurement very recently, with some different technique, and in 2015 they concluded the tunneling time is real in Attosecond science. So these experiments were done on many electron systems, and as I said, there are two components in time delay. One is with laser atom interaction, and another is from correlation, because it's many electron system. And all these systems were many electron. Even helium atom has 2 electrons. So to nail this down and to resolve this issue finally, what is needed is experiment on hydrogen, truly 1 electron system. It's very difficult to do this experiment because hydrogen atom and they tend to form a molecule. You have to break the molecule, then do this experiment. And this experimental group, they reported the first measurement, and we're very happy to have Satya, who gives us a talk on this subject. He will tell a little more, so I can skip some details. But the idea is that this measurement was supported by very accurate quantum mechanical calculation by several groups. On theoretical side, what we can do, we can turn on the Coulomb field of the hydrogen atom. We can tune the Yukawa potential in such a way that the width of the tunnel will be exactly the same. And if we turn off the Coulomb potential, the tilt angle becomes immediately 0. And from this, we can conclude that the measured tilt angle has nothing to do with the tunneling time. It's just the effect of the Coulomb field. And to support it, we came up with a very simple model. We call this Keldysh-Rutherford model. So we take the Rutherford scattering formula, and we feed the Keldysh tunneling width as an impact parameter to this formula. And this Keldysh-Rutherford formula, it gives you very nice, if you look at the solid line here, it's the prediction this is prediction of this Rutherford scattering formula, and this is empirical feed to the experiment. So it's not only qualitative agreement, it's quantitative agreement. So we believe that there is no tunneling time, at least in the hydrogen atom. And we can actually feed this Keldysh-Rutherford formula, and it explains that's prediction of this formula. Offset angle becomes larger if you increase the frequency of the laser light, and becomes smaller if you decrease the ionization potential and laser intensity. And so it goes like this with intensity, it goes like that with ionization potential, and it goes like this with the frequency, and intensity dependence is also can be described quite accurately in other atoms. These are atoms from hydrogen, from xenon to helium, depending on their ionization potential. And doing atomic physics with your stopwatch is a great fun. That's the end of my talk. Thank you.
Let me first of all thank the organizers of the meet conference, particularly Pranava, Deshmukh, Bhas Bapat, and Sunil Kumar, for giving me an opportunity for me to give this talk. There was a reference to atomic, molecular, and optical sciences. I used to say that AMO science, which I believe all of you will agree with me, is the mother of all sciences, because AMO is a medium through which we interact with nature. And in all the other sciences, basically it comes to AMO, which to really retrieve the information of what is really happened and understand it in our frame of reference. So from that point of view, AMO is the mother of all sciences. Now, electron molecule resonance, which I will be talking about, is a fairly old area of collision physics, more than 50 years old. But recent advances in experimental techniques and other findings have come out with some very interesting aspects of electron molecule resonances, which has important applications to the day-to-day life even in many instances. when you talk about electron molecule resonance, basically it is chemistry. An electron interacts, comes and gets captured to a molecule from a transition state, and then it's evolves into products. So that's what I'm going to talk about. So it is low collision physics is what I'm going to talk about mostly is going to be physical chemistry or chemistry. So when you talk about negative ion resonance, let me give a, for many physics students, they may not be aware that atoms can form negative ions with the energy lower than the neutral plus free electron state. So this is defined by the electron affinity. So electron can be accessed by a neutral atom and be confined in a neutral atom by the polarization potential induced by the electron, extra electron with the rest of the atomic electrons in the system. So that's how you get for many atoms and many molecules you have a what is defined by this positive electron affinity, you can have a stable negative ions. So of course in neutral atoms you have a large number of states which till we reach the ionization limit, and but in the case of negative ions, for most of them the excited states essentially lie in the continuum. So here you have a large number of excited states you can have, but here there are few, even there are few systems with bound excited states, but generally all the excited states are lying in the continuum. So this is very short lived. So this is, if you look at it, these time scales are nanoseconds or larger for these states, or here it comes to this excited states or the negative ions are much smaller, it comes to femtosecond, hundreds of femtoseconds. So to study these negative ions, as a result you can't use conventional optical spectroscopy. So you have to use collision, electron, mostly studied through electron collisions. Of course you can also do photo detachment of a negative ion to study these excited states of these negative ions. So when to just just to put things in perspective, let me talk about the time scales involved in molecules. You have rotation which are larger than picoseconds, you have vibration ranging from 10 to 100 femtoseconds, and electronic time scales of electron motion, as you heard in the previous talk, it comes in the attoseconds. This is just to give a reference to some other thing which I will be talking about. So electron molecule resonance, so basically as I said, is the electron comes and interacts with a molecule and it gets captured, forming a negative ion resonance, and this negative ion resonance can then decay. It is a very short lived state, as I said, femtosecond, hundreds of femtosecond typically the lifetime. It can decay by ejecting the electron, forming an AB neutral plus an electron. Now this, if I have written E different from the initial energy of the electron, this is E0, this E will be less than E0 because there will be some energy deposited in the molecule AB in terms of vibrational, rotation or electronic excitation of this species. So that is what happens here. When it decays, it is not necessary the electron comes out with the full energy, it would have lost some energy, leading to the excitation of the molecule in vibration or electronic states. Now this being a molecule can also decay through another means. Of course this process can be studied, this is a resonance scattering and it can be studied by electron spectroscopy by looking at the electron and this kinetic energy of the electron and its angular distributions, etc. We can study this scattering process. But being this molecule, it can also decay by dissociation. So when you dissociate, what you get is a neutral fragment or a negative ion fragment. Of course it could, if it depending on the molecule, if it is a polyatomic molecule, it could have more than one neutral fragments, but necessarily you get one negative ion fragment. So this process where you get a negative ion after electron attachment, we call it dissociative attachment, and this is studied using negative ion mass spectrometry. Recently another possibility have been discussed. So that is, you have a dissociation process of this resonance simultaneously with an electron ejection. So here what you get is two neutrals plus a outgoing free electron. So this has been proposed in two papers recently, and it is called a bond, they named it bond breaking by catalytic electron. So there is a electron here acts as a free electron here acts as a catalyst, it comes and reacts with this molecule, and this catalytic action of the electron breaks the molecule into neutral products. So, when you in this talk mostly I will be talking about this process of dissociative attachment. So, one of the important aspects of the dissociation when you look at the dynamics of this is the cross section, how the cross section for the process evolves. So, let us look at the process itself. Here what I have plotted is a neutral molecule AB, the potential energy curve as a function of potential energy as a function of internuclear distance. Now, you have this when the electron comes and interacts with this molecule, you have the vertical arrows defined what defines the vertical, not vertical dashed line which defines the Frank-Condon region, and its electron gets captured in this particular internuclear distances, and the corresponding energies electron get captured to form this AB minus star. Now, this I had taken as a purely repulsive state of the AB minus the resonance state. It need not be a purely repulsive, it could have a minimum also, and which eventually a minimum like that it goes to A plus plus B minus. Now, on its way out it can auto detach shown by the arrow A, or it can as of course dissociation shown by the arrow D, and it forms A and B minus, and the electron ejection is possible only up to the point internuclear separation RC, beyond which you can have a electron ejection. So, this vibration, and all along you can have this decay. So, as a result you have a population of vibration levels in AB, excited levels in AB. So, then when you look at the cross section dA cross section can be written as a product of the capture cross section and the survival probability, that is the probability for crossing this point so that a B minus can be formed. I am sorry. So that a B minus can be formed. So, that is an exponential function written by the two lifetimes, the time for dissociation and the auto detachment time. So, these two time scale determine how much of B minus is formed. Now, because this exponential nature of the two time scales and there are two competing processes, you have very strong isotope effect in this dA cross section. You can see people have seen large temperature effects, temperature dependence, because if you have a subject molecule to large temperature, it can be initially it can be in a vibrationally excited state, and suppose it is formed here, then there you have a Frank-Condon region comes up from here to here, something like that, and from here it can escape much faster. So, the cross section goes up with the initial vibrational excitation. So, recently we have also found that this electron attachment process, the capture process, and eventually the dA cross section is it has a functional group dependence, and this can be used for example controlling chemical reactions. This is a paper which I will be talking about later in my talk. So, this paper discusses this particular aspect of it. So, what are the factors which determines the attachment? So, of course, collision energy. For a given molecule, it does not happen at all energy, it happens only at the resonant energy, particular energies at which the electron attachment occurs. And of course, one of the important aspects is even if the energy is matching, the directional approach of the electron with respect to the molecule is important. So, this happens to the basically to the orbital angular momentum involved, or the orbital angular momentum which the electron is going to bring in while getting captured to the molecule. For example, here I have given an example here of water. So, these are the 4 orbitals which are important in forming resonances in water. This is the highest occupied molecular orbital in water, and 2 other orbitals which are lying just below that, and these are lowest unoccupied molecular orbital in water, and the 3 resonances in water are related to exciting this particular electron in this orbital to this orbital by the incoming electron, and the electron loses all the energy at getting captured into this orbital. So, basically you have a 1 hole 2 particle system. Similarly, you can have a resonance by exciting an electron from here to here, have a again one hole 2 particle system, or a third resonance again from this exciting this orbital to this orbital and getting captured, forming again a one hole 2 particle system, which are basically Feshbach resonances. Now, this and the probability for the electron getting captured as a function of the angular approach have been calculated by the group in Lawrence Berkeley lab and University of California Berkeley. So, they show that this entrance cell amplitude as a functional angle, for example, you can see that this is for the B1, A1 and B2, which really show that the sort of interaction which the electron needs to have with the initial orbital. So, that is in order to excite it has to have spatial overlap, then only you can excite. So, that is this again reflects that apart from the apart from the orbital angular momentum which the electron has to bring in, it also reflects the how much of interaction the electron has to have in order to get captured. So, there are factors which are affecting attachment. So, this angle dependence for a diatomic system have been written down quite some time back. So, you can write for example, the angular dependence for the electron attachment. So, you have it can be written in terms of spherical harmonics and with a coefficient which depends on the electron momentum k, and this mu here which you write in is the difference between the final the orbital angular momentum of the final the resonance state and this out of the neutral state, and the mu of course is a projection of the orbital angular momentum along the principal axis of the molecule, and the angular momentum of the electron which goes from mu to infinity in principle. So, this there are after this there have been other papers extending this theory to polyatomic molecules, triatomic molecules here, and Reid has given a paper written a paper which covers molecules of various symmetries in determining the angular dependence in electron attachment, and recently this have been discussed for few atom molecules by Ramanujan. So, the orientation depends of electron attachment. I am giving an example of H2 here. H2 in its ground state has a symmetry, I mean state is singlet sigma G plus state, and in such a state if the negative ion formed is a sigma G plus state, again you have it is allow any orientation of the electron is attached, because this is a S wave angular momentum of the attaching electron is 0. So, that says that any direction of the electron attachment is possible with respect to this molecule is allowed in the case of attachment. But if you have to form a resonance with sigma u plus symmetry, you need to is a p wave, the angular momentum of the electron needs to be 1, incoming electron needs to be 1. So, that limits in this case the orientation or the electron molecule with respect to the electron beam in this direction. So, like this you can write down this for the various other states of the negative ions. For example, these two I described, and you can have a pi g state, you will have a distribution in terms of angle orientation in like this, or if it is a pi u state, orientation will be like this. Of course, the 0 represents the electron beam direction. So, this is electron beam is coming down like that. So, the orientation, so the molecule with respect to the electron beam is given here. I am showing you this which I will be coming towards the end of my talk again. So, now when you talk about this is I was talking about the electron orientation of the molecule with respect to the incoming electron. Now, that what is the relevance of that in terms of angular distribution of the fragment ions? In a gas, all these experiments are done in high vacuum, where you inject few molecules into the vacuum system. So, this is a gas, and these molecules are oriented isotropically in all possible directions. There is no orientation, selected orientation in the gas space for our molecule. They are in all possible orientations, and when an electron beam comes and interacts and it attaches and it breaks apart. There are, assuming this molecule doesn't, after attachment, doesn't undergo any rotation, you can see that this direction of ejection of B minus, if you were to determine, to measure, it will tell you what is the orientation of the molecule with respect to the electron attachment. So, by measuring the angular distribution of fragment ions, it tells us about the negative ion states which are involved in the electron attachment process. So, I said that the molecule should not be rotating after the electron attachment and before it dissociates. That is called axial recoil approximation. It means the direction of the dissociating bond should not change from what it was before electron capture. So, that means the rotation is negligible and negligible molecular angle changing vibrations. So, one of the nice example which recently have been observed is that, take the case of water. For one particular resonance, it has been found that the axial recoil approximation is not held, because ideally in order to hold the axial recoil approximation in particular case, you should have expected H minus ejection in this direction, but on one of the resonances in water, it is found that it is dominated in the ejection 90 degrees. That is coming through the before the dissociation really fully happened, there are bending mode vibrations in the water molecule, which basically ejects preferentially the H minus in the 90 degree direction. So, this is a deviation from the axial recoil approximation. So, how do we study the resonances? So, of course, as I said, you can do that by electron spectroscopy and electron angular distributions, negative ion mass spectrometry, which I am going to talk about. We can study it by mass spectra, what sort of negative ions are coming, the ion yield versus electron energy tells you about what are the resonance positions for each type of ions. You can measure the absolute cross section, which are again important in discussing the dynamics of the process, and it is also important for various applications. And of course, the momentum distribution ions, this tells you a lot about the dynamics and the structure of the negative ion state. This could be extended by, these studies can be extended by looking at the neutral fragment. So, it is not necessarily a diatomic fragment, it could be it is not be a diatomic molecule, it could be a polyatomic molecule. You can have a diatomic or other triatomic fragment, which if you can detect them, you can see what and study them, you might be able to tell us what are the internal energies of the system, which many of which we may not be able to get from by looking at the momentum distribution ion, which I will be talking about. But there is only one paper which has just appeared this year, 2017, trying to detect the neutral in this process. And all this, what we are talking about, can be done with changing the molecule in this initial condition. So, I said I gave you an example of a vibrationally excited molecule. If you are a heated molecule, you can have a large change in cross section for dA, and the dynamics also could change if you have to initially change the molecule through vibrational excitation or electronic excitation and then do the electron collision. So, this is something again have a lot of applications in plasma sciences, because in plasmas there will be molecules, not just a neutral ground state, but there will be electronic or vibrational metastable state, which can play a very important role in the overall chemistry of the plasma. So, the negative ion resonances basically again is I am going to talk about in the context of chemical transformation. As I said, it is the whole process itself is a chemical reaction, but more than that, how the products of the reaction or the electron attachment process or DA process is important for other in general for chemistry. For example, this is the most efficient mechanism for production of molecules in excited vibrational electronic states, radicals and ions, negative ions I meant here. Provides a method of breaking molecules at low energies. So, you do not have to even at instances there are zero energy electron, thermal electron can break a molecule, even for energies lower than the chemical bond energy, you can break a molecule. because that happens because the electron affinity of the system of the negative ion which is being formed. In this case, for a neutral dissociation A plus plus, you can see this is the energy, minimum energy needed, but in this case smaller. So all these things leads to it gives a lot of it's a significance to what really happens the low energy electron molecule collisions. So this has applications in industrial and laboratory plasmas, planetary atmospheres, astrophysical body. Basically the astrophysical body is a warehouse of all molecule, how the various molecules are formed in interstellar medium. That has a lot to do with the way the radiation interacts with matter, secondary electrons are formed, this secondary electron, how they interact through resonant attachment in creating reactive species and eventually creating bigger molecules. This is another important aspect which has made this electron molecule resonances a lot of attention, interesting, and it has created a lot of attention in radiation induced damage and therapy. It is important nuclear waste storage and disposal and nanolithography. So I am going to run through some examples. For example, this halogen containing molecules are very important in plasma etching processes for creating semiconductor chips, and in Earth's atmosphere, for example, the aurora, which is again this has a lot to do with low energy electron molecule interactions, and as I said, creation of various molecules in space, even neutrals, cations, anions have been observed, and this particular paper gives a fairly good account of this. It is not a review, but it gives a nice description about what are the interesting things which is going on in this. So the radiation damage, one of the recent papers which by Sanch showed that the DNA strands can be DNA can be very effectively damaged by electrons of energy below 10 eV, and these electrons of energy 10 eV are very important because even if you put in any high energy radiation into matter, what you eventually end up with is a very large number of low energy electrons. So effectively they put together, they play a very significant role in the damaging the biological tissues, and this could be used for even controlling the radiation therapies using this based on this understanding. So in nanolithography, for example, this is one of the technique which is a lot of research which is going on in focus electron beam, using focus electron beam to create nanostructures. So here again in high energy electron beam which is focused to few very small size on a surface, and of course you have put in a gas which is typically metal organic molecules are injected, and this secondary electron which are produced reacts, and here there are DA process and various other process occurs, and it helps in creating the nanostructures. So there is a lot of activity going on in studying DA for various metal organic molecules towards application in focus electron beam lithography. I am going to start with the main part of my talk by giving two examples of role of negative ion resonances in planetary atmospheres. So one is a new channel for O2 production from CO2 on early Earth, and second is the production of highly rotationally excited O2 minus from ozone. So what was believed is that in the early Earth, the O2 is produced basically by a recombination of oxygen atoms through the help of a third body, and here you get a O2 in an excited state which then decays to give O2 in the ground state. But recently there is a paper which showed that for using 12 eV photons you can you can break CO2 to give a O2. So this was published in 2014, and using electron attachment you can, it was shown that you in the DA process you can have a C minus and O2 in the ground state again by this group recently in just 2 years back. So, I will be talking about that particular paper in Nature Chemistry. So before that I would like to say what is the technique they used to identify that process of that they could by using electron you can get produce O2 from CO2. So this is a technique which we developed at TIFR about 12 years back, and the first author Nandi is here. He will be giving a talk later. So basically what we use the velocity mapping technique, but we modified for appropriately for using with low energy electrons. The idea is you produce this negative ions here by interaction of electrons with the gas beam, and these ions are then velocity mapped onto a 2-dimensional position sensitive detector, and the Newton sphere as it comes and propagates, it propagates and eventually strikes the detector. You get a time of flight spectrum here, but if you look at the central slice of this time of flight spectrum and look at the position, you record the take out the position of hits on the 2D detector, what you are going to get is a momentum image of the negative ions. So this is an example of O minus from O2 at 6.5 eV. You can see in this case the electron beam is going in this direction, and you can see that there is a preferential orientation at around 45 degrees and 135 degrees complementary parts for the production of O minus or O minus from O2 or attachment of the electron to the molecule. So this is a technique which this Chinese group used. Here they looked at the momentum images of C minus as a function of electron energy, which is plotted here. So you can see at 15.9 eV, I don't know if it's visible at the back, 15.9 eV to 19 eV, there are various images seen. Now here when you get C minus out from the CO2, you can have two processes. One is O2 plus C minus, or you can have a O plus O, O and O, two O, separate O atoms and C minus. The central blob corresponds to that particular process where there is a 3-body breakup and you have a C minus coming out. So that C minus will not have much energy, kinetic energy. So the size of this away from the center, the radial distance depicts how much of energy is involved, is this C minus has at the time of formation, and of course this is the angular distribution which shows. In this case the electron beam is going from going in this direction from left to right. You can see that this particular images, they represent vibrational states of O2 which are being created, and they could use, looking at this process, modeling this process, they said that there are two pathways which produce O2 from this. You have a you have bending mode vibration, and you have two oxygen atoms coming together forming a vibrationally excited O2, and the central C atom is ejected in that direction. Or you can have a roaming type reaction in which you have again O2 being formed. So this is an example of how the new experimental techniques which could be used for understand a new pathway to predict a new pathway to the formation of oxygen in early Earth. Now let me talk about the second one, that is the O2 minus, a new very interesting thing which we observed at TIFR. We found that O2 minus in highly rotationally excited states can be produced from electron collision with ozone. So this is the dA cross section from ozone. You have a O minus channel as well as O2 minus channel. As a function of electron energy, it is plotted here. When you do ozone measurements, you don't get pure ozone in your experimental system. You have mixture of ozone and O2. So you have some signal, in this case quite a major signal of O minus from O2 coming here at this energy, but there is some signal from O minus from ozone also in this case, in this part of it, but it is the dominant part of O minus from O3 you can see here. and here again O2 minus. This entire signal has to come from ozone, there is no other way. And I am talking about this now, imaging of O2 minus. So, these are at images which are taken at lower energy for O minus and O2 minus. But most interesting part is here at the higher energies at between 7 and to 10 eV. So, what we are finding is that at around 8.5 eV onwards, you have O2 minus being formed with very low kinetic energy. Now, if you put in 8.5 eV and you look at the reaction O2 minus plus O in the ground state, the threshold is only 0.6 eV. The excess energy as a result is something like 7.9 eV. So, 7.9 eV now has to come out in the kinetic energy of the two fragments O minus O and O2 minus. You expect some O2 minus with a certain amount of kinetic energy, you can't have a thermal energy distribution. Of course, there you can see that some part of it is being formed with a kinetic energy, finite kinetic energy. So, if you can have a O in the excited state, you can have a 4.2 eV. So, you can have up to you can remove 4.2 eV, but still you have an unaccounted energy of 3.3 eV, because even assuming the O2 can accommodate 0.44 eV. The O2 has an electron affinity of 0.44 eV. So, you add these two together to this, eventually you need to worry about 3.3 eV unaccounted. So, these are the O2 minus potential energy curve which are shown here, taken from this particular paper, and so we use those to calculate. Okay, before we go, let me give an example of a well known, I mean this is rather the but only system which is known for rotation stabilization. H2 neutral, H2 molecule does not have a positive electron affinity, but people found that H2 minus in can be formed in a specium spectra source, and in order to describe the results, this idea of rotational excitation of rotation stabilization was introduced. So, this whole results in this case, basically you have a shifting of these curves. So, you have a system where basically because of rotational excitation you have a shifting in these potential energies. In addition to that, you have a barrier which is generated. So, that you have a local potential in which the system is stabilized and it has a finite lifetime. So, that is why we want to detect the H2 minus state. So, same idea we apply to the O2 minus case. You can say that O2 minus could be stabilized in order to get at these energies. It is 3.6 eV, these two together. This is the coming from the vibrational energy and this is coming from the rotation stabilization. You can take care of the energies to get O2 minus being formed. But so the question was, how do you form O2 minus with such large rotational angular momentum from O3? So, eventually we realized that it can be done only by some sort of a roaming reaction which gives a large rotational excitation to the O2 minus state. I go to two examples where DA to a molecule where it is used in plasma, related to plasma processing. One is CF3I and one is CF4. Here, so let me go to the CF3I. What we are trying to show here is that on electron attachment, this is the CF3 product from CF3I. We are looking, this is a resonance as a function. You can see the peak at around 3.8 eV, and these are the images taken, and there are two structures in this. So, each of these corresponds to the iodine being formed in the ground state, and this is correspond to iodine in the excited state. Iodine can be in the doublet in the P3 half or P half states. So, corresponding now if you look at this, outer sphere correspond to I doublet P3 half, inner sphere is I doublet P half, and we find that 95% of the intensity is in the outer sphere. So, the branching ratio wise, this is what seems to be dominating. The P3 half seems to be dominating. Now, when you go to the compare with the photo dissociation, you can see that when you have a photo dissociation, you have from CF3I, you have these states triplet Q0 and singlet Q1. These are major states which release to photo dissociation. And these two curves do not cross because they are different multiplicity. So, you have a though there is larger cross section for this process for this, so that all that end up in the P half state. So, you have a in photo dissociation you have a iodine being formed in the excited state is a larger probability as compared to iodine being formed in the ground state. But when you have electron attachment, what you have is both these states become are doublet states, because electron brings in spin half and this triplet becomes doublet and this singlet also becomes doublet. So, you have two doublet states and which leads to an avoided crossing. Because of the avoided crossing, what you have here is that the ground state of iodine have a far more probability being formed as compared to iodine in the excited state. So, this is an interesting example where electrons and photons behave this almost same way, but there is a distinct difference in the way the molecules are broken up. Now, the interest in CF3I is because it is supposed to be a better etchant. It can be used as a better etchant because it is supposed to have much shorter time scale in the lifetime in the Earth's atmosphere. So, that will be it has least greenhouse effect as compared to the CF4. That is why interest in using CF3I. In the case of CF4, what we found that when you take a molecule, highly symmetric molecule like CF4, so the molecule with a large symmetry in terms of nuclear structure, the electronic states are generally mostly can be degenerate. Now, this degeneracy can be lifted by having changes in the nuclear distortion, nuclear structure. So, this in using optical spectroscopy, there have been several examples where this effect, which basically is called the Yan-Taylor effect, has been discussed. But there have been few examples where you have electron collision, such effects have been seen. In one of the example is CCl4, where at zero energy electron attachment, it have been shown, it have been at least indicated that it is due to basically a Yan-Taylor effect, which is maybe playing a role. And similarly, in electron collision with the benzene, again it have been talked about. In our experiments on methane, we again show indication of a Yan-Taylor effect in the DA process. But this example gives a very clean example of Yan-Taylor effect in these systems, in this system CF4. So, what we have shown here again the momentum distribution of F minus and CF3 minus, and we plot them and try to fit them for various excited resonance states. And what we find is that if you use only TD fit, we do not get very good fit for both F minus and CF3 minus. Until and unless you use a combination of TD and C3V, we do not get a very good fit. You can see especially this difference at the two poles, the 0 degree and 180 degrees much strong, this effect is, this difference is much larger in this. So, it shows that even in order to explain this the observed angular distribution, we need to invoke the combination of the TD and C3V symmetries. So, I have been talking about electron as a basically for chemical transformation. So, here I would like to give an example of electron attachment as a tool for chemical control. There have been several experiments in gas and condensed phase in this context, But one of the experiment, one of the results from our lab which seemed to have a lot of impact is the following. I am showing some typical results here. You take acetic acid and look at the H minus formation from that. You have 3 resonances, and you can deuterate the acetic acid selectively on particular site and look at the H minus and D minus, and you can, from this data you can see that this particular is in this case D minus is being formed only at these 2 resonances dominantly, and the third resonance is dominantly formed from the carbon side. So, what we are trying to show here is that changing electron energy we can selectively break a CH bond or a OH bond. That is what is shown here. So, this is, of course, we extended this to other molecules like alcohols, for example. We found here again you have a selectively we can break, these 2 are selectively coming from the oxygen side, OH bond being broken, and this is coming from the CH bond breaking. And in ethanol also similar story is repeated, and you can see that the resonances, though there are changes in the slight changes in the resonance, there again there are 3 resonances we can see, and this can be modeled in terms of the precursor molecules. For example, in the OH site, the activity of the OH site can be modeled in terms of what is happening in water, and similarly what is happening in the methane side. The CH side is methyl side can be modeled in terms of the methane electron attachment. So, we repeated this measurement for amines. For example, here again we could see the effect of the localized effect of the resonance and its selective fragmentation. So, from this result what we find that the electron attachment depends on the functional group of the molecule, functional groups present in these molecules, and this can be used for selectively breaking molecules at different sites. For lack of time I do not want to go into more details of what the process, what the dynamics, etc., but this is the bottom line, that you can selectively break the NH, CH and OH bonds using electron energy as a control parameter. So, towards this how much time I have now? How much? 4 minutes. It can't be, is it? Sorry. Okay. I am sorry. Yeah. Okay, I am sorry. Yeah. I thought I should speed up. So, I want to come to some of the recent results, which very interesting result we found on electron attachment to H2. Here this is a very nice example of quantum dynamics of 5-particle system, because you have 2 protons, 2 electrons, there is an extra electron which is coming and interacting and modifying the H2 breakup. So, H2 has 3 resonances, one at 4 eV, one broad resonance between 7 and 13 eV, and one at 14 eV. And these have been explained in terms of 3 states, resonance states, one a sigma u state which at decays to H minus plus H here, and there is this broad one is represented by this purely repulsive state. You can see this being very steep potential energy curve gives rise to a larger electron energy range for the negative ion being formed, and this particular one is believed to be a sigma g plus state which decays to hydrogen the N equal to 2 state and H minus. There should be an H minus here which is missing. So, now when we look at this, we are going to concentrate on this part of this particular resonance, and okay, before that let me just to recapture what we discussed. When you have a electron, when you look at the angular distribution for the electron attachment and subsequent fragmentation, you can express in terms of spherical harmonics, And if there is, this is only one resonance state is present. If there is more than one state is present, you can have a linear sum here. So which mean, what it means is that you can have only even or only odd partial waves are allowed for, for being captured. So this prevents forward backward asymmetry in the electron attachment process or the fragmentation process. So that's because that means if in a homonuclear diatomic molecule there is no direction dependence, whether it is coming from the forward or backward direction, it should not affect. So this again which I showed you earlier. So when we did the measurements on H minus from H2 and D minus from D2 at different energies. So here I am plotting, this is the data, the momentum distribution from the first resonance at 4.5 eV. These are taken from the third resonance for H minus, and this is for the D minus from D2. I can see that these images are quite distinctly different, and these are a very strong forward backward asymmetry. But when it comes to D2, there is a bit of an asymmetry present, but that is not very strong as compared to that is in H2. But here again the asymmetry also seems to be changing direction. Here for example, unlike H2, in the backward direction seems to be larger in density, this is almost equal, and here it seems to be going in the forward direction. So how do you explain this? So this can happen only by breaking the symmetry of the system. The homonuclear diatomic molecule has an inversion symmetry, that inversion symmetry has to be broken. So it can happen. So when you have, if you have two states, two resonances being formed simultaneously and in coherence. So for example, if you have a sigma g state to sigma g, use an s electron capture. So you have a, I can write the angular distribution in terms of half, like a half sigma dA for a Garrett state. And for a p electron capture, you have get a sigma u state, and the cross section for that will be a dependence like this, cos square theta distribution. Now if these two states were to be created coherently, what you are going to get is a cos theta term here. You have to sum the amplitudes and take the square. So you have a cos theta plus a plus cos theta, you get a whole square, you get a cos theta term. Here I have written another term here, delta, there is a cos delta, the delta is the phase difference between the two channels. So you can get in principle you can get an asymmetry because of this cos theta term. So that sort of explains that, but what it needs is that you have to have a coherent excitation of two resonances. So the question is, why is D2 different from H2? So one of the reason is that D2, the main reason here is that D2 has a smaller survival probability. You can see the absolute cross section for D2 is smaller. Here is the ratio is something like 600. Here is a factor of 10 or so. Here is a factor of 3. So that means that's because D2 being heavier, it takes more time to dissociate. By the time it dissociates, the electron ejection is competing against the dissociation, so it has less probability for forming as a surviving the resonance, has less probability for surviving to give D minus from D2. So that is one of the reason for the D minus being different from D2. Now we can look at in terms of potential energy curves. I said these are basically the two coherent states are created, two states are coherently created, a sigma g and a sigma u state by electron attachment, which then traverse through two different potential energy curves to dissociate to the same limit, H minus plus H2L. So we start with the same point and end with the same point. So you have a, basically here again you have a quantum interference. Depending on the interference, here you have two different paths, the wave packet is traversing through two different paths, so you correspondingly you have the quantum interference. So the effects again will be different depending on the what the potential energy curves are, and you can get you can see that in the case of D minus, the amplitude, final amplitude is smaller, it is because the survival probability, and you can have a so it is the system here is like that. You have a two arms of an interferometer, optical interferometer. If you put in absorbing media with a different absorption coefficient, it is similar to that system. Such a system, this system is very similar to that. What is happening here? You have an interference, and this interference amplitude also will be different depending on the how much of the absorbing medium, absorbing coefficient of the medium. This asymmetry which you measure can be then calculated using model potential energy curves. So, we are giving an example of two different types of potential energy curves. You can get the interference in terms of asymmetry parameter. And here what we have taken is the sigma g seems to a lifetime 8 femtosecond from electron scattering measurement. So, we have to assume sigma u lifetime which is not known. So, we have plotted sigma u lifetime as the electron energy in this case to get this intensity. The color determines the asymmetry parameter. So, this model seems to be better suited for what we have observed in this case in our measurement for this particular potential energy curves. And let me conclude by talking about another aspect which I talked about BBC. We found a experimental evidence probably for resonant production of CO2 from formic acid, which show that BBC is indeed happening. But let me conclude my talk by saying what are the future directions. So, one of the theme would like to continue where we have been trying to do some measurements on excited molecules and radicals, but there is a lot more to be done, and actually it has just begun, and it will be very exciting to do work on prepare molecules in vibrationally electronically excited state and then do electron attachment. We would like to, I believe the functional group behavior has to be probed further, and diagnosis of neutral fragments as shown in this particular paper. It will be worthwhile to proceed again to understand the DA process. And high resolution imaging. Currently the imaging technique which is used is resolution is something like at the best half an electron volt. It will be worthwhile to improve this resolution to something like 100 milli electron volt, which is the vibration spacing for molecules, which will be worth pursuing. And of course, there have been measurements on condensed molecules in clusters and condensed phase, but imaging techniques if you could use for this experiment that we it will produce it will come out with a lot more very interesting information. STMs is another thing. Scanning tunneling microscope have been used for probing atoms and molecules at a very microscopic scale. It has been shown that STM can be used for single molecule engineering. Here again, basically what is really happening is the DA process at play, or electron molecule resonances at play in exciting a molecule or even breaking up a molecule, etc. So, this is something which one could use at single molecular level. There have been few experiments, it will be worth pursuing. And last one I would like to talk about this temporal dynamics of the negative ions using ultra short time scale using pump probe techniques, which you could one of my colleagues M. Krishnamurthy have been talking about initiating such experiments. He did start, but it did not take off, but hopefully he will be able to do that. These are the direction which I believe it's worth going forward in this. So, I would like to conclude by thanking many of my collaborators, students and postdocs which are listed here. Thank you very much for your patience.
Role here, one as the president of the society and as the co-convener with Pranav. And let me begin by thanking both the directors, Professor Ganesh and Professor Satyanarayana, to have invited the society to hold its meeting here with a very, very generous financial and administrative support for conducting this conference. I really have no words to thank you sufficiently for this very, very generous gesture on both your parts. And a conference like this is really very, very hard to organize unless everybody around you is willing to pitch in. And this has been done extremely, with a great friendship, with a great bond of friendship from all colleagues at both IIT Tirupati and IISER Tirupati, and also the administrative staff at both these places. And very often what happens is that when we meet for a conference, we do end up meeting our faculty colleagues and students and postdocs and so on. But many of the people who work in the background remain faceless. I want to express my thanks to them, very sincere thanks to them. And in particular, there are a few people who I would like to name, but this is not just an exhaustive list of people by any means, by any stretch of imagination. But I just want everybody to realize that this should not be a set of faceless people. So I'll just mention a few names: Chaman Mehta and Inderpreet Kohli at IISER Tirupati, and their entire team working with them, and the similar bunch of people at IIT Tirupati led by Adinarayan and Shivkumar at IIT Tirupati. And most importantly, the support we have had from NPTEL for recording this, the plenary sessions, which will ensure that this conference doesn't get forgotten so easily even in the electronic medium. And I would like to thank the media who were present here for the inaugural session, which will also ensure that our conference gets coverage in newspapers and the electronic media. Finally, as you already know, Springer has agreed to bring out the proceedings of this conference, and I would like to thank them for this offer. And I'm sure we'll be able to do this in a good time. Soon after the conference begins, we'll start soliciting your articles based on your talks here, and we hope to put these proceedings together as early as possible and within the time frame that we have set for ourselves. And last, or perhaps this should have been the first, all you delegates who took time off from your schedules to come and join us for this conference, faculty members, students, postdocs from not just the entire country, but quite a few. I mean, this is a refreshingly large participation from people from all around the world, including actually people from the antipodes of Tirupati. And this is really as far as you can go across the globe. You can't get further than that unless you want to fall off. So let me welcome all the delegates once again, and thank everybody who has pitched in to get this conference to a very good start. And I hope that the next 2 or 3 days will be very productive, and we'll see everything happening smoothly as it has gone off so far. Thank you very much, and let's assemble in 30 minutes.